Ladies and gentlemen, Dr. John Belkowitz here from Intelligent Concrete. Wanted to review a set of series or a set of tests that we ran using an alternative supplementary cementitious material under ASTM C1709 called Juno XP. Juno XP is a product that we've worked on many times before. It's used to give you something called value-added performance. Replace a lot of cementitious using a little bit of Juno, make up your yield using coarse aggregate or fine aggregate. One of the things that we saw when we first started working with Juno XP is we were on a residential job, and I think this is published in one of their blogs or articles that we've got going on, or that they've got going on. But we were running a job site, residential job. It was the beginning of the summer, excessively windy. We get anywhere between 20 and 30 mile an hour sustained winds out here. It's kicking up a lot of dirt, a lot of dust. And what we saw at that top surface was just elephant skin, alligator cracking. The top surface was just tearing open from that rapid loss of moisture. When we used the Juno XP, we couldn't change the 20, 30 mile an hour sustained winds. We couldn't change the sun. We couldn't change that evaporation rate. But what that Juno XP did was, as we see here in a bit, it changes how the concrete responds to that rapid evaporation. And of course, the reason why we care about that is concrete cracking. And the impetus of this video today is to identify the type of concrete that manifests from that rapid heat and evaporation loss. And you have all these different types of crack: volume changing, thermal shock, plastic, drying shrinkage, and shrinkage that develops from loading or shock loads. The type of cracking that we're talking about is that plastic shrinkage, where you have a rapid loss of water from your surface, your subsurface, and your body of the concrete, and with that comes a certain volume change. Because you're working with a slab, there's a restraint on the bottom. So with that restraint, with that volume change, and that movement, plus that restraint, you have these built-up stresses that ultimately overcome the strength of the concrete, causing that concrete to crack. And what exacerbates that, if somebody's trying to bull float or finish or broom that concrete while it's going through this phenomenon. So what we do is we use a test here in the lab to actually mimic that environment to see how our change in concrete mix design, it's really a mortar, but how that change in mortar, using those different additives that we have, in this case Juno XP, will change the response of that mortar in that aggressive environment. So the aggressive environment we have, it's a 48-hour cure at 100 degrees Fahrenheit, 32% relative humidity, with a certain wind speed over it. So we see an evaporation loss of 2.4 to 3.2 grams per hour. And we have to calibrate that for every position that we're using. There's 3 positions in our chamber, and each one of those 3 positions has a mortar sample. And that mortar sample is a 25-inch squared, 3/4 of an inch thick. The mold itself is 1 inch thick, but the sample that we make is 3/4 of an inch thick. And it also has this prism that is rigidly connected to the mold. And what that does is it acts as a crack focal point, or a crack location point. So we know no matter what, we're going to create the environment where the mortar is going to want to crack. We're causing something that's called a singularity, or built-up of stresses, and increasing the crack length between the top surface of the mortar to the top surface of that prism. And what we do with that sample after 48 hours is measure the crack length at the bottom of the mold, the middle of the mold, and the top or the front of the mold. And we compare the length of those cracks and how that crack has changed compared to a reference. So this is an A to B comparison, and we do this using optical microscopy, and then we come back with something called image J analysis, which allows us to do a line fraction analysis, and then from there, of course, we have calibration that tells us how big a pixel is in that optical microscope. And then we come back and do that comparison. So what we've got right now is 2 samples, one which is a straight Portland cement, and the other one is 5% replacement of the Portland cement with Juno XP. Now please bear in mind, normally when we use Juno XP, we're getting a major reduction in total cementitious, like a 20% reduction of cementitious, and then we're putting 5% Juno in and making up that yield with our coarse and fine aggregate. But for our testing, specifically under ASTM C1709, we have to stick to this prescriptive method. And what you see here is basically how these two different samples, and these are 1 samples out of 3 samples that were used for the sample set, we can see that there is a major change in the size of the cracking. You can barely see the crack, although a crack is still there, in the Juno XP at 5%. And ultimately what we see here is that despite the fact that we're getting an increase in degree of cement hydration, and we see that through our increase in strength, through our compressive strength, but we're also getting a reduction in pore water migration that allows for that water to migrate over time, and of course that volume change. We see an increase in the toughness of the hydrated cement matrix to resist the residual shear and tensile forces from this aggressive environment. Not only the heat and the evaporation loss, but that restraint that we're seeing. And ultimately the volume change that occurs to cause the crack in the reference, that same response mechanism is not happening with the Juno XP enhanced mortar, or at the very least it's not happening to the degree that is going to cause a major crack as we see here in the reference. And ultimately creating an environment that's going to create a concrete that is stronger and lasts longer, because when we can remove the tendency for our concrete, or reduce the tendency for our concrete to crack, we're reducing the porosity, reducing the permeability, ultimately increasing the density of not just the hydrated cement matrix, but the entire concrete composite and the concrete body. And when it comes to the continental United States, our biggest reason for ripping and replacing concrete structures from premature failure is due to steel corrosion. And a lot of that steel corrosion comes from concrete cracking and failing prematurely. By using the Juno XP, you can make that concrete stronger and last longer, and ultimately increase that service life. So yeah, hopefully you learned something. Let me know if you have any questions, concrete concerns. Don't forget to like and subscribe. Ding that bell for notifications. Go concrete! Beat asphalt!